slower and less intense for you. All right. All right, so this class is called Principles of Programming. It is going to continue on from your 1301 class. So we're going to Java. So we're going to start off reviewing everything. We're going to probably cover terms that you guys already know, but it never hurts to hear them again. We're going to start the labs and stuff in the book. Should have already started you doing just basic input, output, typing things to the screen, that sort of stuff, right? So just some general terms that you should have gone over in chapter 1, defining what a program is, programs just a set of directions that the computer is going to follow. We build up the directions, we give it to the computer. The computer takes those directions and runs the code, and it gets broken down into machine language and goes into the processor. Yes. So input is whatever data or information we give to the program to make it useful. It could be from a keyboard, it could be from a file, it could be a database. Any information that goes into the program to make it run is input. Not all programs have input. Some of them run without any. A process is going to actually do the computations. It's going to do the math if it's a math program. It's going to add values. It's going to actually do something, perform an action. Output is the opposite of input. So anything that the program puts on the screen is output. You could print something as output. You can save output to a file. But anything that in the program interacts with the screen and gives information back is considered output. Programs use a lot of variables, so we're going to make sure that you understand how to use a variable, declare a variable, store information in a variable. Since Java is very much a typed language, we're going to make sure you're using the appropriate data types when you're creating your variables. We are going to do a lot of what they call computational thinking in here. One of the hardest things, in my opinion, when teaching someone to program is teaching you how to think like a computer. Because breaking the problem down into the core components that you need to build it back up into a program, sometimes it's the hardest part, especially if you have one of those really artistic brains that thinks in less concrete fashion. Sometimes it's harder to wrap it around what computational thinking or what the concrete parts of a program are. I don't have this problem because I think very concretely and have no artistic ability whatsoever. So it's just learning how to break everything down into all the little minute pieces that you need to build it back up. This is where algorithm building is very helpful. And we're going to talk about algorithms and building that plan. I'm going to tell you straight up that 30 minutes of planning will save you hours of frustration when you start coding. I'm still very much old school. I do my planning with a piece of paper and a pencil because I like to draw diagrams and I like to have a visual representation of what I'm doing. You don't have to. I'm not going to make you turn in algorithms and grade them. But one of the first things I will ask you if you get stuck on something is, what's your plan? How are you planning on solving this problem? So if you haven't done some planning, I might grab a piece of paper and a pencil and start talking you through it that way. Or if we're online, talk you through it on the computer. I'm a visual learner. Questions so far? Have I bored you all to death? I will try in the future not to have such text-heavy slides, but I was just trying to get, like I said, I'm visual. So programs very much are like a recipe. So if you've ever looked at the cookbook or you looked at a recipe and you're cooking your own food or you're watching somebody cook, inputs, ingredients, the things you need to make that dish are the inputs to the program. The directions on how to put those ingredients together and produce the dish are your methods and your procedures and your functions. The output is the finished dish, whatever you're going to feed yourself and your family. So if you think about it like that, and you start planning through when you're reading an assignment or a project that I give you, first thing I usually do when I was in a program details given to me is I go through it and go, okay, what information do I need to make this successful? What inputs do I think I'm going to need to be getting from the user or from somewhere else? And I make that list. What are the desired outputs? What is the user looking for when I turn this program into them? And I make a list of those. And then I start planning how to get from input to output. That makes sense? Now, the way I get to the final product and the way you get to the final product may be completely different paths. There is no one correct way to program any program. So I've been told often that my approach is not the way that most people would have done it. That's fine. If you've got a better way of doing it, I'm okay with that, as long as you meet the requirements of the assignment. I don't care how you got there, as long as you have all of the required pieces. More definitions. Seems like the whole first chapter with a whole lot of definitions and a whole lot of terminology. Like I said, we're going through this pretty quickly because you should have had 1301 already and seen these terms. Again, programs usually start off with a main method. The main method is the driver of a very simple program. Somewhere in your program, there's going to be a main that runs it, right? Statements end with semicolons. Those of you that came from a Python background are going, why do I have all these semicolons? Because Java needs semicolons. The scanner is a text parser that will take input from the screen or from a file and break it into usable data for your program. I am summarizing these definitions. Are you going to have to memorize these definitions word for word and repeat them back to me? No. I'm never going to make you write out definitions. I might give you a multiple choice question and actually pick out one. If I'm really feeling crazy, I might put a matching together for you. But straight memorization, not really my style. Scanner next int means it's going to go get the next integer. These should be some functions that you've seen and some library functions and library method calls that you should have seen in 1301, or at very least seen in the labs that I assigned for chapter 1 if you've done them. My family hasn't got used to me working again. System.out.print, you're going to see this a lot because it's how you print things to the screen. And I'm going to encourage you to use print statements to help you debug your code. Debuggers are great. It was a big program. But if you use a small program, sometimes it's faster just to put some print statements in to find out where it went wrong than it is to set up the debugger and watch it run. You know, if you are just trying to add a couple of numbers and you're not sure you're getting the right result, you can just put a print line in and have it print to the screen what the result is. And then you're like, okay, that's not right. I need to fix it. Or, hey, that is right. Maybe the problem's further down. I have been guilty of putting in print lines that said, got this far, made it here without crashing on the bigger programs, just where I know where to narrow in my focus of where my logic went wrong. Loops, especially, because that off by one counting on loops can be a bear. A string literal is anything inside of the double quotes. That's the literal string that you're turning in. New line, I usually do the system.out.print line with the ln because you want it to go to a new line or it all prints together. The new line characters are great for setting up and structuring your output. A new line character usually is a formatting tool. So like, depending on which programming language it's in, it could be a /n or something like that, kicks you to the new line. Obviously, I'm new to YouTube, so if you get these videos and they have weird things in them, send me a suggestion on how to fix it. White space and comments. We are going to use comments. I don't know what the department's stance on it is right now, but I came through here for my master's degree and my undergrad degree, so I'm firmly believe in comments. You should take advantage of comments, especially if you're in my class, because if you did something and you're not sure why it doesn't work, or you did something really you think's off the beaten track, if you give me a comment explaining what you were trying to do, it's easier for me to give you partial credit. It's also easier for me to debug where you went wrong. Single comments are the 2 slashes. Multi-line comments are a /* to begin them and a / to end them. If you want to do Java docs, I think it's a /2 stars, and it'll create a Java doc for you. I like comments. There's no reason not to comment stuff, especially if you think you're going to have to revisit it, because I promise you, next semester, you won't remember why you did something that way this semester. White space, obviously, is any blank space on the screen, not necessarily white. I know a lot of us use dark backgrounds and stuff, but it's empty space. Java doesn't really care that much if you put extra spaces in. I know that some of the guidelines that the department uses tries to keep methods to a shorter amount of space, and that program that counts those lines will actually count the empty ones. So put them in. If it makes it easier for you to read, take them out when you're done. This is not like Python. I'm not going to use tabs and stuff it doesn't care about, but be aware. I'm old, so the easier you make it for me to read, happier I am. Errors and warnings. You obviously have done some coding if you're in here. Syntax errors, Java is going to help you find. It's going to know when you violated the rules of the Java language. It's going to underline it, highlight it, something, right? Logic errors are so much harder to diagnose, and that's where your debugger is going to come in handy. It's going to help you watch and see if the variables have what you expect them to have in them when they get to that point. It's going to help you find where it goes off the rails. I will help you with logic errors as much as I can. If, either online or in class. But don't wait till 11:30. The night is due at 11:59 and expect me to answer your email. Because I'm probably going to be asleep. Not always, but probably. Compile time errors. Those are things that are going to show up when you compile it, and it's going to, memory leaks, things like that. Most of the errors are going to be found in the syntax errors or the logic errors. You'll see a few compile time errors. When we run across those, we'll work through them. Warnings. Those are things where it's going to give you a message saying, hey, you need to be aware of this. It's still going to compile. It's still going to run. But it may not be doing it the most efficiently or the most ideal way of doing it. So warnings, be aware of them, but it will still proceed. Questions? One of my classes is actually going to talk back to me today. So how do computers process your code? Computers are going to take what we do in the IDE, and I am going to ask you to do Eclipse at some point because the projects will be done in Eclipse. I will put together some information on how to download and install Eclipse if you don't already know how to do that. But the IDE is going to take the high-level programming language that we're using, Java, and it's going to compile it down into machine code that the computer can process. So we talk about bits and bytes. Those are the ones and the zeros, the ons and the offs of your computer. So if you know your computer history, computers started off as switches, and they turned switches on and off to indicate what they needed to do or what they needed to add and subtract. Those 0 indicates that the switch was off. 1 indicates that the switch was on. And here's your random trivia for the day. If you look at your power button, it's a circle with a line in it. That's because it's the 0 with the 1 superimposed over it, on and off. In the dark ages of computers, when I first got into them, your power button actually was a toggle switch on the back of the power supply of a computer. You guys are probably not old enough to remember those. And it had a 0 for off and a 1 for on. So there's your random trivia. Where did the little symbol come from? It's a 0 and a 1. 8 bits or a byte. I'd be happy to show you how to convert decimal numbers to binary numbers if you're interested or haven't already figured that out. So it converts, our IDE is going to convert our high-level language into something that the processor can use, usually machine code. It's not 100% ones and zeros, it's registers and different things like that. But it's going to take it down into individual pieces to do calculations and steps. And your processor does millions of these calculations and steps a second. Processors started off really, really big. ENIAC, which was one of the first computers used during World War II, took up a whole room. Nowadays, all that processing power can fit on the tip of a pen. So computers get faster and smaller about every 18 months. They usually double their capacity and speed, while also the processors getting smaller every time. They tell me that eventually, that's Moore's law, they tell me that eventually will not be the case because we'll eventually not be able to get stuff small enough. But so far, in the 20 plus years I've been doing this, it has held true. Memory. Memory makes or breaks a lot of your programs. The more memory you have, the more processing you can do at a time. In the dark ages of computing, when I came through, we actually had to optimize all of our code to use as little memory as possible. Because my first computer at home had 256 megabytes of memory in it. Y'all are probably got 8 or 16 gigabytes of memory in your laptops. Your cell phones have more memory than my first computer at home had. So the memory is a temporary place where all those processes running through your processor get swapped in and out of. It's a temporary. Memory is temporary, storage is more long-term. So your hard drive is storage. Your RAM is memory. So the RAM is what's being used while it's processing and running. If it's having to switch to your hard drive, then it's not a very efficient computer or you need more RAM. Your hard drive is for storing things that you want to keep semi-permanently. We won't call it permanent because hard drives often fail. So,
So you said RAM is more
yeah, RAM is random access memory. That's what RAM stands for. So it is what your computer uses while it's running the program. So it's swapping the instructions in and out of RAM to the processor as it needs. And it's doing it super fast.
so that's more short term.
That is short term. As soon as the program stops running, everything in RAM goes away. Anything called an executable program means that it has the machine instructions to go to the processor, to use it, to do something. Now, as you probably all know, it's because it execute doesn't mean it did exactly what you wanted it to do. But compilers are used to break that stuff down. So the list of terms are off here. We've talked about them, maybe not in the order they're on my slide because I don't tend to read slides directly, but questions about anything? All right, let's take a little tour of the inside of your computer and the outside of your computer. Everybody knows what a screen and a keyboard is, right? Disk or hard disk, like I said, is that place that you're going to store things. It's where you save Word documents. It's where you save things that you're going back to again. RAM, random access memory, temporary holds data and gives it working space for your process. Your operating system, this is Windows, it's Safari on Macs. I'm not a Mac user. So this is the Mac OS. There's a couple of Macs in the room. So this is what makes your computer run. It boots it up. It gets everything running. It stores all your programs. It's the manager of your computer. It interfaces with the internet. It interfaces with your input and output devices. You can kind of think of it as like the office manager at a big building. Knows where everything needs to go and how to get there. The cache is also a small amount of RAM that the processor moves things back and forth to. Cache memory is on its own chip, separate from your RAM. But if you're looking at buying a computer, it tells you how much cache it has. It tells you how much, well, it used to tell you all these things, bus speeds, things like that. The amount of cache memory you have is important for how fast your processor is going to run. How quickly can it swap things in and out? The bus is the cable that connects all your memory and your processor together. And the faster that is, the faster it runs. If you have a really small bus, it'd be kind of like sucking mud through a straw. It can slow everything down. Clock speed, that is inside your processor too. It keeps up with how much time each instruction has had in the processor, and then it swaps it out. So it's not really processing a whole bunch of instructions at the same time. It's just rapidly swapping between instructions where it looks like it's simultaneously doing it all. And it does it so fast, it does it in nanoseconds, that it gives you a smooth performance. Now, modern computers have more than one processing core going at the same time, so those are doing more instructions faster. Transistors, these are the old way that engineers used to do it. You'll see little transistor switches inside of your computer on the motherboards and stuff. Don't touch them. It's easy to short out a motherboard. Done it a few times. They were really integral part of older computers when you were talking about a single processor and you didn't have the multi-threading and stuff we have now. They're still used a lot in electronics. So just a brief history of some of the languages. When I came through, the primary language for the computer science program in the 1990s was C. And I did a little C++. And then my senior year, there was this new thing that we did a senior project on called Java. And I personally didn't do well in Java because I was so familiar with C. Took me a little while to wrap my mind around it. So Java came into being in 1991. It gained popularity through the 90s. Sun Microsystems was the original company that produced Java. It's now Oracle. Oracle bought out Sun several years ago. It is still one of the most popular computer programming languages being used. It was created to be general purpose. It is class-based, it has an object-based, so it's reusable. You create pieces and you can reuse them and not have to recreate them over and over again. It doesn't have a lot of dependencies. It was one of the first languages, or was the first language that was cross-platform compatible. So if I was running a Mac or a PC, it didn't really matter because it all ran on the Java virtual machine. It doesn't have to be recompiled every time you changed operating systems. And of course, about that time, the internet was growing rapidly. So it was great for internet applications because it didn't matter what computer was at the end of the transmission, because as long as it had the Java virtual machine in the background. They typically do compile in bytecode that runs, like I said, on any architecture, but that was new. That was unheard of at the time. I learned to code in a very procedural coding languages. So C had what we call pointers, and you'd have to allocate and deallocate the memory you were using in your program, or you'd run out of memory. You'd use up all the RAM. Java doesn't do that. Java has what they call garbage collecting. When it's done with a piece of memory and RAM, it just automatically sweeps it up and reallocates. That was mind-blowing at the time because you weren't having to make sure that you released memory that you had allocated to a list or an array. So like I said, programming is largely about problem solving. We're going to talk a lot about how we're going to solve a problem. I think that's one of the most key factors to being good at computer science is being able to process and solve the problems put in front of you. Because you may not go into programming, but knowing how a program is put together will help you when you're trying to protect those programs in cybersecurity. Or if you're doing data science, knowing which programs are going to best manipulate your data are going to be useful. We call it computational thinking. So this is something we've been doing, you guys probably did in your science classes earlier. It's kind of like the scientific method kind of thing. You're going to break it down into component pieces, think logically about it, and put it back together. That's all I have for today. Do you have questions? Concerns? How many of you, well, I'm gonna go ahead and stop the video, but how many